So what is the law of conservation of energy? Energy is neither created nor destroyed. That's the poetic way to say it. You can only transform energy from one form to another. This means if you're looking at a closed system, and by a closed system I mean one with no outside sources of energy. You're not adding a battery to the system. You're not putting a motor in the system. You're not adding gasoline to the system. If you are looking at a closed system, the total energy you start with has to equal the total energy you finish with. We talked about two main types of energy: kinetic, a half mv squared, and potential, mgh. The poetic way to say this, Elias, is when the Big Bang happened, the amount of energy in the universe has never changed ever since. By the way, the Big Bang violated the law of conservation of energy. It did, but we're not sure. Basically, our laws of physics for about the first trillionth of a second after the Big Bang don't work. But after that, they all seem to work just fine. Okay? Let me give you an example. Both the potential energy, so both the kinetic energy and the potential energy of a block freely sliding down a ramp are shown below only at the bottom of the sketch, but we can fill in the missing values. At the bottom, how much potential energy do we have? Why? Because mgh, h is 0, so on the ground is 0. How much kinetic energy, energy of motion, do we have? What's our total energy? Be obvious. What's our total energy? 75. What's our total energy? 75. The law of conservation of energy says that can't change. So at the top, if I wasn't moving, how much potential energy must I have? If my total energy has to be 75. Yep. As we slide down the hill, we lose potential energy because, Braden, we're losing height. How much kinetic energy do I have if I only have 50 joules of potential energy? It has to be 25, because what does my total have to be, Alec? 75. By the way, I slide further down. As I slide further down, I speed up. I get more kinetic energy. I lose potential energy. How much potential energy would I have right here? 25. Yeah. Now, of course, normally the numbers aren't that easy to do in your head-ish, but this is the concept. The total energy you start with equals the total energy you finish with. The law of conservation of energy, I often abbreviate it as C of E, says the amount of energy in a closed system never changes. Or as an equation, the stored energy initially and the motion energy initially equals the stored energy at the end and the motion energy at the end. The total you start with has to equal the total you finish with. If I want to write that with symbols, because I tend to abbreviate, PE initial plus KE initial equals PE final plus KE final. This is the law of conservation of energy. I gave it to you on your purple sheet, I think, I think, on your formula sheet. Yeah, okay. Yeah. This is the law of conservation of energy. This is what allows us to analyze roller coasters. And we will by the end of today's lesson, I hope, if I get that far. We can be even more accurate because in real life, you almost always are losing some energy to heat. So you can modify it by saying the amount of stored energy you start with and the amount of motion energy you start with has to equal the amount of stored energy you end with, the amount of motion energy you end with, and if anything's missing, it must have gone into heat. That little tweak, special subversion, I didn't put on your formula sheet. You can put it on your purple sheet if you want to. Great example of this is a skateboard half pipe. Analyzing this with forces and projectiles would be very difficult because, can you see the angle changes depending on where you are on the hill, and so your components would change every split second. It can be done with calculus, those of you that have taken calculus, but why bother? energy is a scalar approach. So here's what I'm going to do. I've turned friction off, and I'm going to give us a little bar graph so we can see what's going on. I'm going to give this skater potential energy. See it in blue? And gold is the total energy there. Okay? The total energy won't change. But what will change is how it's spread out. At the very bottom, your potential energy will be 0, so your kinetic energy will be at its max. In other words, you'll be going your fastest at the bottom of the ramp, which, Diego, you've clued in playing on the playground as a captain obvious, but there's the physics of why. At the top, for a split second, how fast is the skateboarder traveling at the top for a split second? So all of the kinetic energy is 0. All of the total energy is potential. Okay? Now, this would be in a perfect world where everything was 100% efficient. That is not the universe we live on. So now I'm going to turn on friction just a tiny bit. And you're noticing another bar slowly increasing. Those of you at the front might be able to read what it says. Emma, can you read what that red bar is called? Thermal heat. Okay? In real life, if you're ever on a skateboard half pipe and you don't do anything, slowly what happens is the energy that you put in, the potential energy that you started with, slowly ends up in heat. Unless you add energy by shifting your weight at the right time and pressing down at the right time, but then that's no longer a closed system. Now there's an outside energy source, the food that you ate from your body. Okay? This is a great example of the law of conservation of energy. Which one didn't change? The total. That's the law of conservation of energy. Okay? The total doesn't change. You can transform energy from one type to another. Okay? Basically, energy's got to come from somewhere, it's got to go somewhere. So I said to you, this is my go-to when people ask me questions. As an example, superhero movies are big right now. So let's look at The Incredible Hulk. Great example. Even if gamma rays could somehow make you turn strong and green, when the Hulk, for example, throws a car, he's giving that car potential energy and kinetic energy. That energy has to come from somewhere. It would have to come from the Hulk's body. The Hulk would have to be eating 24/7. The Hulk would not have time to be the Hulk. He'd have to be eating all the time to get the energy in order to give the energy to the other objects. Okay? The law of conservation of energy is what makes, sadly, most superhero movies unphysicsy. Pardon me? Yeah. Oh, I have a marble energy transfer device. I have to pause the video. So the key idea is potential initial plus kinetic initial plus potential final plus kinetic final. And if you've lost anything, it goes into heat and sound, but we lump that all into heat because we're not going to be that specific. Bouncing a basketball is a great example of an energy transformation. At the top, what type of energy do I have right now? Potential. Where will it have no potential when it hits the? Where will it be moving its fastest then? When it hits the? Why? We can think of it in terms of gravity and acceleration, but you can also think of it in terms of energy, because all of the potential had to go somewhere, and most of it went into kinetic. Although, could you hear it? And so that's why it won't bounce to the same height that I dropped it from. I lose a little bit. I also lose some to heat. Those of you that have played basketball, those Saturday morning tournaments, you may have noticed when you take the basketballs out there cold, how do you warm them up? What you're doing is you're actually adding heat to the air inside because some of the energy is definitely transferred into heat. Okay? So bouncing a basketball is a great example. Pile drivers are great examples of conservation of energy. You give a pile driver potential energy, and then when you release it, it turns into kinetic. So let's do some with this equation. A projectile example 1A, next page. A projectile is launched straight up into the air. If its initial velocity was 75 meters per second, how high does it go? You could solve this using VI equals question, or well, D equals question mark and A and all that, but you can solve it with energy. You can start out by going kinetic initial plus potential initial equals kinetic final plus potential final. I can't remember whether I wrote potential first and then kinetic or kinetic first and then potential. Braden and I flip-flop, but it's initial plus initial equals final plus final. What was the equation for kinetic energy? It's on your sheet. You'll probably end up memorizing that because you're lazy, but you don't need to. So I guess kinetic initial would be a half mv initial squared. What was the equation for gravitational potential energy? Yep. So potential initial will be mgh initial, and then it's going to be a half mv final squared plus mgh final. It said ignore friction. That's physics code, AJ, for ignore heat. Usually right around now I pause and I ask, are any of these zeros? When will kinetic energy be zero? When V is zero. So imagining this particular situation, is there ever a time when V is zero? What have I called the highest point in this equation? Final. Yes? So we can go like this. Ha-ha! In fact, really, if I really knew what these equations were made of, I could have crossed it out on that line already. What about potential energy? When will potential energy be zero? When our height is zero. Is our height ever zero?
Yeah.
When?
H
initial? So I could have crossed this out. I could have crossed out PEI. Well, of course, PEI is not a real province, right? It's an island. Not a premier. They're a mayor at best, right? Yeah. So what I really end up with is this. 0.5 mv initial squared equals mgh final. Oh! How many terms are there? 2, one on the left and one on the right. Is there an m in everything on the left? Is there an m in everything on the right? Cool. What was I trying to find? So how would I get the h final by itself? Divide by g. H final is going to be, and you can write it a couple of ways. You can either write it 0.5 vi squared over g, or I probably would have written it as vi squared over 2g. I would have left the 0.5 as a fraction, as a 1 over 2, and does putting a 1 in front of anything really make a difference? No, those are identical equations, but what do you get? What do you get? Should be fairly high. 75 meters per second is pretty fast. It's about 170 miles an hour. 200 and some kilometers per hour. Emma, what'd you get? 187? Anybody else? Yep. 287? Meters. Okay. You could have solved that with Physics 11 kinematics, VI, VF, D, and A. And I probably would have if the question hadn't said use energy. But what you can't use kinematics for is B. Suppose you do the experiment and you notice that it only reaches a height of 125 meters. How much energy did you lose to air friction? Or if you want to think about it a different way, how much work did air friction do in slowing this object down? Okay. What's this asking me to find, Cole? How much what? Okay, how much heat energy? This is conservation of energy. So again, and G. I'll go KE initial plus PE initial equals KE final plus PE final. But this time, I'll add heat. I'll do it in red so it looks like heat. Are any of these zeros? So kinetic energy will be 0 when you're stopped. Are we ever stopped? Again, I think at the top for a split second. Gravitational potential energy is 0 when you're on the ground. Are we ever on the ground? I think we started on the ground. Again, PEI. And so what we really end up with is this. A half mv initial squared equals mgh final plus heat. Cole, what did you say they want us to find? How would I get the heat by itself? Yeah. By the way, a common sloppy mistake, and I don't know why, kids divide by MGH. Even though there's a plus sign there, don't do that. But just every year, I have 1 or 2 kids, I give them a question like this on the test, and they get the heat by itself wrong. So subtract. I'm going to get this. Heat, I'll do it in red, equals a half mv initial squared minus mg final. Does the m cancel this time? Why not? No, I'm in heat. Okay? But otherwise, it's plug and chug. Complicated plug and chug, but plug and chug. Heat is going to be 0.5 times, what was m? 75? No, what was m? 12? V initial was 75, right? Squared minus 12 times 9.8, not negative 9.8 because work and energy are scalars, so we don't put the negative in here, times 125. How many joules of energy were lost to heat? I really encourage all of you to try typing these into your calculator because they're going to get longer and more cumbersome, so you want to make sure you know how your calculator works for these calculations. Sorry? What was your question?
That's like, I couldn't see the...
You should be able to figure it out yourself by looking at the numbers you have in front of you, right? I wish I was clever enough to write messy on purpose so that you had to look at the numbers in front of you instead of just blatantly copying without thinking about it, but I write messy just because I write messy. So I'm going to get 0.5 times 12 times 75 squared minus 12. Shh, quiet, please. Thank you. Do you get 19,050?
Yeah.
Okay. Heat is a form of energy. What are the units for energy? Joules. Ooh. Calvin, what's C want me to find? Huh? What did we find in part B? I'm going to give you, we didn't find air friction because friction would be a force measured in, what was this measured in? I'll tell you what we found. We found the work done by friction. That equals 19,050. Hey, Calvin, what's another way to write work? Work is what times what? Force, you say. Which force? Air friction. See how we're being clever? We can write this as the force of air friction times distance equals 19,050. And so suddenly we're at a situation where we can actually find air resistance without using the complicated air resistance equation, which I've never given you. It involves cross-sectional area and density and a few other things, but we can work around. How would I get the force of air friction by itself? The force of air friction is going to be divided by, what was the distance? This would be the average friction. It might not be constant. In fact, probably wouldn't be, because as you slow down, air resistance gets less. This is giving us an average, but still, it's a start. And I get the average force of air friction was about 152.4 newtons. Mr. Dewick has a very, very cool demonstration of conservation of energy, but I'll stop the recording. Yeah. So, here is the key. When would I use the law of conservation of energy? So I've tried to build in your physics brains almost habits. Like, did I say angle? Everybody? Okay. I've tried to build some certain habits so that when you run into something, you think a certain way. When do I use conservation of energy? When there is a change in height, a change in speed, and especially when there is a yucky, curvy path. Skiing and roller coasters being a great example. Ski slopes and roller coasters. Okay. So example 2, at location Z, a skier is traveling at 18 meters per second. How high up the next slope can the skier reach if we ignore friction? Looking at this question, is there a change in height? Is there a change in speed? Is there a yucky, curvy path? That's a job for conservation of energy. And so I'm going to start out by going KE initial plus PE initial equals KE final plus PE final. Do they want me to include heat? Diego, what does it say in brackets? No, okay, ignore heat. And you know what? Skiing, not much friction. We'll be close. Before I go further, are any of these zero? Kinetic energy is zero when the skier is stopped. Is there ever going to be a situation, initial or final, when the skier is stopped? Yeah. Well, how high up? This is like the skateboard ramp. At the top, the highest they can reach, they're going to come to a stop. So absolutely, I can go, aha! You can put a little equals 0 if you're wondering what we did, but if you cross it out, I'll figure it out. Oh, potential energy will be 0 when we're on the ground. Are we ever on the ground? Yeah. Where? Initial or final? Yeah, because by the way, I might have wanted to go initial, and I might have wanted to put a little I and a little F there, just so I know what I'm looking at. And yeah, I agree with you. Of course, PEI is not a province. I mean, no, it cancels out here. Okay. What is the Sarah equation for kinetic energy? So I guess kinetic energy initial is going to be a half mv initial squared equals. What's the equation for potential energy? And so potential energy final is going to be mgh final. Oh! Is there an m in the first term? Is there an m in the last term? Can little kids and grown-ups go skiing together? Really? Well, that's handy. What are we trying to find? Okay, as far as I'm concerned, I can either give you the initial speed and say how high, or I can tell you how high and say what was the initial speed. What I can't ask you for is the mass, because it's going to cancel. So how would I get the h by itself? And I'll get the final height is equal to vi squared over 2g. Yes, there's a 1/2. You can put the 1 in front of the vi if you really want to, but why? By the way, if you see the squared on the v, if you ski twice as fast, you'll go 4 times higher. Okay? I told you that square dominates your life in ways you don't realize. So it's going to be 18 squared divided by 2 times 9.8. I can almost do that. The answer is going to be really close to 20-ish. Because it's almost 18 squared divided by 18. Not quite. What'd you get? Oh, 16.5. I corrected the wrong direction. Yeah. Okay. I mean, skiing is fun, but roller coasters are funners, as far as Mr. Dewick is concerned. Let's look at some roller coasters. Well, actually, before we look at roller coasters, let's look at the bow and arrow again. So suppose it takes an average force of 245 newtons to pull the bow back a distance of 68 centimeters. Stop. Cross out 68 centimeters. How many meters? 0.68 meters. Nice try, Mr. Dewick. Okay. Alex, what does A want me to find? Oh, work is force times distance. Right? What's the force in this question? Yeah, by the way, the reason I said average force, if you've ever pulled a bow, it's really tough to get it going. Then it gets easier, then it gets tough again. It's not a constant force, so I'm having to fudge things a little bit here. Unless you have a fancy schmancy compound bow, then it gets easier the further you pull it, but that's some really cool physics, but not what we're looking at here. So in case you're wondering why I keep saying average force or average speed. So it's going to be 245 times 0.68. What do you get? 166.6. Now there's another way to think about that. That's not just the work that was done on the bow. That's how much potential energy was stored in the bow. This is not gravitational potential. This is not MGH. This is just stored energy. So how much potential energy is stored in the bow? The potential energy, not MGH, it's 166.6 joules. Okay. I'm going to be I'm seeing a lot of people on phones. Can we put the phones away? There's like 4 people on phones in the last few minutes. You know who you are. Stop it. C. Ooh, Austin, what's C want me to find? How fast? Okay, now we're doing a nice practical question. With previous physics, there was no way we could figure this out, but now we can use conservation of energy. Now, this one isn't so obvious because there isn't a change in height, there isn't a change in speed, there isn't a yucky curvy path, but there is stored energy. So I'm going to write down PE initial plus KE initial equals PE final plus KE final. But it's important, Diego, to realize PE this time is not MGH. It's just the stored energy in the bow. When is the stored energy in the bow 0? After you let it go. In other words, I'm going to argue that my final stored energy will be 0. In fact, do you know where all that stored energy is going to get transferred to? What type of energy? Yes, my initial kinetic is 0 because the arrow is at rest. This is a special subcase of conservation of energy for a bow and arrow, or my Nerf dart gun. Did I just apply a force over a distance? Yes. Did I just do work? Yes. Have I stored energy in here? Yes. If I measured the mass of my Nerf dart, could I figure out how fast it was theoretically going to leave? I've done that. And then I've used a radar gun to measure the speed of this. Turns out this Nerf dart gun is only about 8% efficient because it should leave fast enough to leave a bruise on all of you, and it barely leaves at all. So they've clearly put in a whole bunch of safety features to bleed off some of that energy.
Unless you melt the crap out of it.
Adam, you can look at Adam Savage has done a couple of, he's built a automatic repeating Nerf dart gun where he removed the safeties, and it goes pretty fast. Yeah, go ahead. Meanwhile, I'm not going to write MGH. I'm going to write 166.6. That equals a half mv final squared. Yeah. Yep. Yep. Yeah, he does good stuff. By the way, I should have also gone like this. 42 grams? No. We don't do physics with grams. 42 grams. How many kilograms? Kilo is tricky. 0.042 because there's 1,000 grams in a kilogram. Here the M does not cancel, which makes sense. A heavier arrow would not leave the bow as fast. A lighter arrow would definitely leave the bow faster. If I try launching a bowling ball with a bow and arrow, it's not going to go very fast at all. So the M shouldn't cancel. Ooh, how would I get the V by itself? How will I move the M over? How will I move this 2 on the bottom over? Times the 2. Divide the 1. Will dividing the 1 make a difference at all? So I'll get this. VF squared equals 2 times 166.6 divided by 0.042. Or if you don't like the 2 on the top, you could have made the 1/2 a 0.5 and you would divide by a 0.5 on the bottom. Same thing. Did I hear somebody say squared? So, yeah. What do you get? I was trying to make up some pretty good numbers. I looked up some specs for this, so I'm hoping we get a reasonable answer. If we get 1,000 meters per second, I'm way off. 28.1? Is that right? That doesn't seem right to me.
Yeah, I got
89 point? 89 point? So 89.1? You know, the football field is about 100 meters long, so this arrow would travel the length of the football field in 1 second. You know, that's about the speed of an arrow. I've seen arrows shot. You can follow them with your eyes, but you got to be quick. It's not like a bullet that you can't follow with your eyes. So that seems like a good ballpark figure to me. Okay.
I made the 0.
Yeah. Okay. So yeah, my Nerf dart gun works just like this as well. This might be a nice application question to throw at you. But, okay. Example 4. A 2 kilogram model airplane is flying horizontally at 22 meters per second. All right, Diego, what does A want me to find? How do I find KE? Got to be an equation. I'm trying to train your eyes to look in the right place now, because this is finally the first brand new stuff we're doing this year. Okay, KE equals half mv squared. Are my mass units good units? Yeah. Are my speed units good units? Yeah. Let's be bold. Let's go straight to our calculators. 0.5 times 2 times 22 squared. And I get 484. What are the units for energy, Diego? Yes. This is how much energy the system has, which means at any point, that has to be the total energy. The plane goes into a power dive and it levels off at 40.5 meters closer to the Earth. Ooh. How much potential energy did it lose during the dive? How do I calculate potential energy, Kieran? How do I calculate potential energy? Yeah. So the potential energy lost is going to be mgh. Did they give me a height, Kieran? Yeah. Let's write this one out since you were a little uncertain. Let's put the 2 and the 9.8 and the 4.5. 2 times 9.8 times 40.5, no squareds. Oh, but I'm missing a times. You get 793.8? How would I show an energy loss? Okay. We lost potential energy, but Sarah, that energy had to go somewhere. This is what the law of conservation of energy says. Where'd that energy go? Yes! The plane sped up. Well, of course it does. When planes dive down, what happens to their speed? But this is why. They're losing potential energy. Of course they're gaining. It's got to go somewhere. It's going to go into kinetic. We're ignoring heat and stuff, but some of it would have gone into heat and things too. But yeah, it's going to go into kinetic. What was your wait? Yeah. That part we don't have the physics to deal with yet. It's true. Well, first of all, this is a model airplane, so let's assume the noise loss is pretty minimal. Big airplanes you can hear from kilometers away. You're not hearing a model airplane from kilometers away. Fair enough? So C says, how much kinetic energy did the plane gain? Gotta be 793.8 joules, because that energy had to go somewhere. It cannot just vanish. D says, okay, what's its new kinetic energy? Isn't it new kinetic energy 793.8? Cool, why not? Oh, it already had some kinetic energy. So the new kinetic energy is 484 plus 793.8. I get 1277.8. And so your point, Elias, is correct, which is why in E I said, if we neglect frictional and sound, how fast is the plane traveling now? Oh, we can do this. How much kinetic energy does it have right now? What's the equation for kinetic energy, Sarah, my joy? So I think 1277.8 equals 0.5 mv squared. Can I get the v by itself? How? How will I move the m over? How will I move the 0.5 over? Okay. Or times by 2, whichever, but you said 0.5, so I went with yours. And then, oh, that would give me v squared. Oh, really? So you're telling me v is going to be 1277.8 divided by 0.5. And what was the mass? 2? And, square root. Divided by 0.5 times 2. Square root. What was its original speed before it dove? 22 meters per second. Now that it's gone into a power dive and leveled off, what's its new speed? 35.7 meters per second. Is that right? What you got as well? Roller coasters, roller coasters, roller coasters. I'm not quite going to get through the lesson. So what I'm going to do is I'm going to pause here. On Tuesday, we're going to finish this lesson, and then I have lesson 6 is more conservation of energy, more roller coasters and places where we can use this. So it's a nice continuation. Then Wednesday afternoon, I hope to finish off the unit, lesson 7. Ideally, you also have a take-home quiz for homework. I'm kind of hoping that your test on work and energy won't be next week, but it'll be near the beginning of the week after. Okay? Generally, this is one kids do pretty well on because it's really plug and chug, no components. You got to know your stuff, but otherwise it's get stuff by itself and carefully plug and chug. And the most mistakes I see are sloppy calculator mistakes. Okay? Playland.